right, friends, we've got two last quick things we're going to talk about. I think maybe I said the last video was the last one, but I mean, calculus is just so fun. So why stop when we're on a ride? In this example, I just want to point out one interesting thing that we could see with it. So we've got volume bounded by this paraboloid surface and then the xy plane, which remember, the xy plane is going to be z equals 0. So again, we would look for the intersection of those two, which is just going to be 0 equals 4 minus x squared minus 2y squared. A little simpler in this one because we're already pretty well set up, right? I could just solve for x squared, which is that 4 minus 2y squared. And then we could go ahead and take the square root. So x is going to be plus or minus that square root of 4 minus 2y squared, which that's all helping me to define this region R, which if we think about trying to draw our region R, what we actually have in this example that we're taking a look at is it's not a circle, it's an ellipse, because notice when if I got these both over on the one side, right, if this was x squared plus 2y squared equals 4, if we got everything so that it was equals a 1, we would have x squared over 4, and we'd have plus y squared over 2 equals 1, which tells me that this is an ellipse. Now, the easiest way to graph it is to just look for those intersection points. So like looking right here, when x is 0, those y intersection points, we're going to get y squared equals 2. So we come up to positive square root 2 and negative square root 2. And then when y is 0, x squared is 4. So x is going to come over to 2 and negative 2. And we have this nice ellipse that I will try and draw. So again, we could define our x's to go from one to the other. Or one thing that's really interesting in this example that we could take advantage of is when I look at my entire volume, my surface that's over top of that region, it's all symmetric. So one of the things that we could do is we could try and simplify by just taking a portion of this region and then duplicating that volume to get the total volume. Like if we look at it, we could cut this whole volume either just in half and double it, or I could cut it into quarters and quadruple it. So let's go straight down to some quarter values. So if we look at something like, I just want this portion of that region. Now we know our x's rather than our y's, so we're going to try and do left curve, right curve. So when we think about x, remember we're going to need this 4 times. Well, x starts at x equals 0, and then it comes over to this right curve, which is going to be the positive semi-ellipse. So we'll come over to positive square root 4 minus 2y squared. And then we look at the y's on those bounds. We're going to see that, well, we started at y equals 0, and we went up to positive square root 2. So when all together, we come up with our volume, well, we're really going to do 4 times that double integral. Now notice we are doing bounded between these two curves, but the bottom curve is just 0. So really we're just doing the integral of 4 minus x squared minus 2y squared. We chose to do dx and then dy, where x goes from 0 to this square root 4 minus 2y squared, and then y goes from 0 to square root 2. Now you do have to be careful that it's not just the fact that our region is symmetric, it's that the volume, the solid is symmetric over that region. So like in the example that we just did, the region over the solid over the region didn't necessarily have that symmetry. So we couldn't necessarily do this in the previous example. But here, this solid over here is all symmetric. We could cut it into those 4 pieces and then duplicate those pieces to get the total volume. So an interesting thing to potentially take advantage of, but use carefully. The last example I want to take a peek at is, what if we're not necessarily computing volumes, but rather just trying to integrate something? So like we're trying to evaluate this double integral, and we notice that we run into an issue. Where look at this double integral, when I try and do sine of y squared with respect to y, I run into the same problem that I did a couple examples ago, where there isn't an easy antiderivative for that. Right? We would probably go to a u substitution of u is y squared, but then I don't have du. I don't have y dy in this integrand. So my u substitution is going to be tricky. It's not going to work. So one of the things that we can do is we can kind of reverse engineer this to recognize that while this is difficult, if it was sine of y squared dx dy, well, in terms of dx, sine of y squared is just a constant. And then likely we'll end up adding in something where we're going to get sine y squared times x. And then probably that x is going to get some y substituted into it, so we might be able to use u substitution in the next step. But I can't just flip-flop the integrals because the bounds wouldn't make sense, right? If I just flip-flop the bounds and put the bounds of x to 1 as my outer bounds, we don't do function bounds on the outside. We have to do functions, and then in terms of those functions, where does the integral go? So what we need to do instead is interpret this as a region, right? When we did our region, our bounds in terms of 2 different things, they were both coming from looking at the picture. So this one never started with a picture, but we can use a picture to help us rewrite it. So we can look at this region. Now we have to interpret it backwards, right? Y goes from 1 to x. From x to 1, excuse me, I wrote that backwards, right? Lower bound to upper bound. So, well, y equals x is this line, y equals x. Y equals 1 is this top horizontal line. So we're really going from the bottom line to the top line, and then x is going from 0 to 1. So we're going from here to here, and we're doing it from this to this, which gives me this upper triangular region. So this was my line y equals x, this was y equals 1. So what we want to do if we're going to flip these is, rather than looking at this region as top-bottom curve, we want to look at it as right-left curves. So instead, let's look at where does x go from and to, and then in terms of that, where does y go from and to. So x, the leftmost curve, is really this y-axis. So x goes from 0 over to the line y equals x. Notice I need it in terms of y, so we're going to say that x goes from 0 over to y, and then y, notice, goes from the quantity 0 to 1. So we can rewrite this as the integral from 0 to 1 of the integral from 0 to y of sine of y squared dx dy. And now this is easier. So it's just a useful technique where we can kind of take our geometric abilities, our ways of interpreting these double integrals geometrically, to also help us algebraically. So understanding both parts of the coin can be a very, very useful thing. So this is where we're going to pause. I know that section 14.2 is a little longer. We got some long videos for you to watch. 14.3 will be a little quicker. We're going to look at some ways of attempting to simplify our work by taking advantage of other coordinate systems. So be on the lookout for those videos, and we will answer your questions as you send them in.